Hello Bearcats. In this instruction we are going to learn about inverse functions. The first thing you want to know is the inverse function of f of x is denoted by the notation f with a little -1 superscript of x. That it means that this is the inverse of f of x. The next thing we want to talk about is we just finished a section on compositions, and if you are given two functions, let's say we're given f of x and we're given f, the inverse of that. You can prove that they are inverses of each other by using compositions. In other words, if you take this and plug it in for this x, and then you take this and plug it in for this x, that would be a composition. That's like your f of f inverse x. So, it's written this way. If you have f of the inverse of f of x, and once you perform that composition, it equals x, and you can take the inverse f of x of f of x and prove that it is x, or it simplifies to x, then you are proving that these are inverses. We're going to verify inverses on our next problem. So let's check it out. The instructions might say something like this: verify inverses. Which inverse function is the inverse of f of x? So to prove that, we're going to do compositions. So the first thing we're going to do is we're going to take the given function and the g of x function, and we're going to do a composition to prove if it does equal x, then they would be inverses. So we are going to do f of g of x. That means we're going to take all the g of x stuff and plug it in for the x in the original function. So this is a little complicated algebra, so we're going to have 5 over, and we have a double fraction here. We have x minus 2 over 5. That's plugged in for the x, and then minus 2. I'm going to write it out. I think it'll help a little bit if you write it out this way. So that is going to equal 5 over 1. That's your 5. And it's divided. That's what this fraction bar means. Divided by. And then I'm going to put in parentheses. X minus 2 over 5 minus, and I'm going to make this 2 over 1. And I think if you write it out like that, your algebra will be better. So now I'm going to have 5 over 1 divided by, and I'm going to find a common denominator. So the common denominator here would be 5. If I make this a 5, I did 1 times 5, so 2 times 5 would be 10. That will have to become a 10. So all of a sudden you have over 5, you have x minus 2 minus 10, because that minus goes with that 10. And therefore, you have 5 over 1 divided by x, and then you have 2 minus 10, so minus 12 over 5. Now, what we're going to have to do is, instead of dividing, we're going to multiply by the reciprocal. So we're going to have 5 over 1 times, and we're going to take the reciprocal of the second term, which would be 5 now over x minus 12. And at that point, we have 25 over x minus 12. There's no way to simplify that to x, so it is not equal to x. It is not an inverse. Okay, let's try. I'm going to do a different color here and see if we can. All right, so let's try now this side over here. So we're going to do the same thing. We're going to try f of h of x. So we're going to go f of h of x, which means we're going to plug in our h of x information for the x. So let's go ahead and try this one. So now we're going to start over like we did a while ago. We're going to have 5 over, and then we're going to have 5x plus 2, and that's replacing the x, and then still minus 2. We're going to write that out, and we're going to make this 5 over 1 like we did a while ago. Fraction bar is just a divide. We're dividing. And then I'm going to put a parentheses here because we have 5 over x plus, I'm going to say 2 over 1. And then we're minusing or subtracting 2 over 1. So we're combining all of that. So now, when we reduce that, we have 5 over 1 divided by, and then look what happens at the top. You have all of this is going to be over x will be our common denominator. So if you make this an x, this is going to be a 2x. And if you make this an x, it's going to be a 2x. But look what happens. You're going to have everything over x, and at the top you're going to have 5 plus 2x minus 2x. So that's going to cancel out. So you have 5 over 1 divided by 5 over x. We're going to multiply by a reciprocal. 5 over 1 times x over 5. Our 5's go out. X divided by 1 is x. It is equal to x. Yippee. Go Bearcats. It is an inverse. All right. Next, we're going to take a look at finding inverses graphically. So the first thing we're going to do is we're going to take f of x equals x squared, where x is greater than or equal to 0. Greater than or equal to 0. So let's go ahead and do a t-table and plug in our information. So x has to, the restriction is x has to be greater than or equal to 0. So we'll start with 0, and this is our original equation. Plug it in and we would get 0. We're going to put a 1 in, 1 squared would be 1. We're going to put a 2 in, 2 squared would be 4. Put a 3 in, 3 squared would be 9. All right, so let's just graph those points. That would be our original function. So we would have 0, 0, and then we would have 1, 1, and we would have 2, 1, 2, oops, 1, 2, and then 1, 2, 3, 4, and then we would have 3, 9. So 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, right there. So this graph of the original function that I'm going to write in red would go something like this. And those key points. All right. Now, for the inverse function, so you want the inverse of f of x, you're going to create a t-table. And the inverse, we just have our x and y values reverse each other. Okay, so they're going to be the opposite. So over here, our y values were this. They are now going to become our x values, 0, 1, 4, and 9. And our x values, so it's like they switch places, are going to become 0, 1, 2, and 3. And then we'll graph this. So let's go ahead and graph these points. Again, we're at 0, 0. Now we're at 1, 1. That's the same. And now we're at 4. 1, 2, 3, 4, 1, 2. All right, and then we're at 9, 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, and we're right there. And this graph now would do this. They are inverses of each other because they would be reflected over the y equals x line. Everything switches. The domain, this would be the domain of this graph, and this would be the range of this graph. And this is the domain, and this is the range, but notice how they've switched. So the domain of this is now the range of your inverse. And the range of your original is now the domain of your inverse. So the domain, they switch out. All right, last, we're going to talk about vertical line test and horizontal line test. We're almost done for today. Vertical line versus horizontal line test. We already know that a vertical line test tells us if something is a function. So for the vertical line test, this determines a function. A horizontal line test is going to determine if there is a inverse or an inverse. All right, so let's take a look. Here's a couple of examples. So if I give you this example, and I give you this graph. All right, I'm going to change pen colors. I'm going to do my vertical line test in red. So my vertical line test, no matter where I go across this graph, it would be a function. I'm going to go ahead and switch and do my horizontal line test in, let's say, blue. So if I did a horizontal line test and I ran that down horizontally, it would pass the horizontal line test. So f of x, the original function, or the original graph, is a function, so it's a yes, because it passes. And then the inverse would also be a function. Oops. So it determines if there is an inverse function. All right, so there can be an inverse, but will the inverse be a function or not? Let me give you a contrasting problem. This time, our graph, we're going to do a quadratic. So what if I have this, and this, and this, and this is my graph. All right, so if I draw a vertical line, it passes the vertical line test, so we know that f of x is a function. Go Bearcats. Now, in this case, if we had an inverse function, if we were to, and we didn't sketch the inverse function, you just get to determine this from the original function. Our inverse function, if we drew the line as a horizontal line test, it would not pass because it would be under that line twice. So this would not be a function. So the inverse will not be a function even though the original graph is a function. Over here, both the inverse and the original graph would be functions. Last thing we're going to do is we're going to talk about one-to-one, and then we're going to find an inverse algebraically. One-to-one is if it passes the horizontal line test. Okay, a function is said to be one-to-one if it passes the horizontal line test. The original relationship and the inverse are both functions. So they have to both be functions. So a while ago, our first example would be one-to-one. Our second example would not be one-to-one because the inverse would not be a function. All right. Last thing we're going to do is we're going to find an inverse algebraically. So I'm going to give you f of x, the original function, as the cube root of x plus 1. And I want us to find the inverse of f of x. All right, the first thing we're going to do is we're going to rewrite this as the original function as y equals the cube root of x plus 1. Hopefully you've noticed a pattern by now that inverses, the x and the y values actually switch places. The domain and the range switch places. So to do this algebraically, we're going to switch our y and our x out. So we're going to make this, I'm going to come over here and write so I have a little more room. We're going to make this x equals the cube root of y plus 1. And then we're going to start to solve. So to get rid of the cube root, I'm going to cube both sides. So now I have x cubed equals, this cube will get rid of the cube root, and you're left with y plus 1. And then I would need to subtract the 1 to solve for y again. So I would get y equals x cubed, and then I'd subtract the 1 minus 1. So our inverse function could be written like this, that our inverse function is now y cubed. That's a y, not an x. Sorry about that. X cubed. Sorry. Get myself confused. X cubed minus 1. And that would be the inverse function. All right, that's it. Go Bearcats.